Very good. And with that, over to you guys. Thanks.
Thank you, Tim. Hello, everyone. This is Ethan Languri of Tennessee Tech University's IEC. I hope everyone can see the screen. The first slide on energy saving the HVAC system, and you can hear me well. So I guess we're going to start with refreshing our minds on some of the basic definitions before we get into some further details. Starting with sensible and latent heat. Sensible heat, as everyone knows, is the heat added or removed from a fluid that results into a change in the temperature of the fluid. For example, heating of water from 60 degree to 212. Latent heat, on the other hand, is the heat added or taken away from the fluid that results into a change in phase, but happen at the same temperature. For example, boiling the water from 212 to 212 steam. So from liquid to vapor kind of phase change. We use dry bulb and wet bulb frequently as well in HVAC applications. Dry bulb is the temperature we measure using a standard thermometer like thermocouples. Wet bulb, on the other hand, is the temperature associated with the moisture content in the air. So if you can manage to make the tip of the thermocouple wet, we can measure the temperature, the minimum temperature we can achieve, which is the temperature of a saturated air. We usually talk about the specific heat and relative humidity. A specific heat is the amount of water vapor in the dry air measured in grains, and 7,000 grains is equal 1 pound. In relative humidity is a measure of how saturated the air is with water vapor, and normally set it as a percentage. So the amount of water vapor in the air as a percentage of the total amount that could be held at its current temperature is called relative humidity, which is a percent. Enthalpy is the total amount of heat, including sensible and latent, all together in the air, which we can use that in order to kind of calculate the energy at any point. Dew point is a temperature at which the air is completely saturated, and kind of above this, we're going to condense the water out of the air. And of course, we use psychrometric chart as long as we can have two conditions of at any state, we can kind of find out the other properties. The bottom axis shows the dry bulb temperature, which usually start from 32 all the way to on the right-hand side over 100. The curve on the left-hand side shows the wet bulb temperature. Relative humidity lines are shown here, that starting from 10%, 20, 30, all the way to 100%, that reports us the kind of wet bulb temperature. The specific humidity, which was grain over the pound of air, you can read it on the right-hand side vertical line, dew point on the left curve. Enthalpy, kind of presented here on the psych chart. And overall is that if you're heating and humidifying, so heating means going along the increasing dry bulb temperature, and humidifying means adding more moisture to the air, which means going along the kind of y axis upward. So this is our direction as we heat and humidify. On the other side, if you heat and dehumidify, you're still going to the right-hand side by removing the moisture out of the air. And number 3 is cool and dehumidify. You're low in temperature, cooling and humidify. We often use ton as a refrigeration ton in kind of cooling systems, that each ton is 12,000 BTU per hour. And that number comes from the amount of energy required to melt 2,000 pounds of ice from 32 to 32, from kind of solid to liquid in over 24 hours. And cooling tower ton is a little bit different. You should add another 3,000 BTU per hour for the heat you have to remove from the compressor compression as well. So that's That's about 15,000 BTU per hour. Quickly, again, reminders on vapor compression, that you have a compressor, you have a high pressure side and low pressure side. So your high pressure vapor after compressor go through the condenser, rejecting the heat, and you condense it, bring it back to expansion valve, and then the pressure and temperature drops. It's ready to absorb the heat from the environment inside the evaporator, and really we repeat the cycle. And we always like to kind of study this on a pH graph as well, pressure enthalpy graph, that you can superheat it and raise the pressure while you go through the compressor at 2.2. At the constant pressure, you condense it all the way to the subcooled liquid. And then during the expansion valve, there's a constant enthalpy process to come down, and then constant pressure, you evaporate it, you're repeating the cycle this way. Efficiency in cooling systems, we report it as a kW per ton. kW refers to the amount of energy it takes that refrigeration cycle operates, and the ton is the kind of useful cooling we provide. And of course, efficiency gets better as we go down. So for package, direct expansion equipment is 1.2 all the way to chillers around 0.5. Can everyone hear me well? I just want to make sure everyone can hear me well. Someone confirm?
Yeah, Ethan.
Oh, awesome.
Yeah.
Okay, I just want to double check.
You're coming through loud and clear.
Thank you. Awesome. So now let's get into categories of HVAC systems, starting with DX systems. That is a direct expansion equipment, utilize a refrigerant for direct heat transfer with the airstream. And this is a package, as you can see, all major components are located in a single outdoor. Really, in my house, we have one of those that everything is in the outside unit, and it's very looking really good in terms of using the space. A lot of facilities use the rooftop package, that everything is located on the roof. You have a duct to bring the air from the inside into the package, and this is how you supply. You have the outside air access in case that either for completely using outside or a mixture. There are split systems as well, that we see those condenser unit outside of the building. The way they work is that they're connected through the refrigerant line. So you reject the heat outside to the air in this case, and then you have the air handling system evaporator inside the building. On the larger systems, chillers, you have the chiller, you have its own refrigeration cycle. On the evaporator side, you have a chill water loop that takes the heat out of the buildings, facilities, process in the facility, and kind of bring it back to the evaporator side to cool it down. And on the other side, the condenser side of the chiller, mostly we're using a cooling tower to reject the heat to a cool water that is exposed to air as well. We're going to go through those details of cooling tower later. Different types of chillers, and each type, it can be worked either with the air-cooled or water-cooled condenser types. Each has their own benefits and disadvantages. Air-cooled are really great in terms of low maintenance. They're closed loop, no problem over really cold ambient winter conditions. Packaged and packed system, so they use really less volume. They can be located
in school.
On the floor.
Still in school.
And And they work great in a low ambient operation, low ambient condition. So if there is a climate that is not too hot, those are really practical. On the other hand, if we use a water cooled, such as cooling tower case, the efficiency is much better compared to air cool. Longer life for equipment, but those comes with a lot of maintenance costs and issues. Such as water treatment, makeup water that should be available, mechanical maintenance. You have to protect it from freezing in harsh winters. And then you have to clean the chiller condenser frequently as well. Here we have a kind of look, we're looking at the centrifugal chiller that there are two shell and tube heat exchangers, one for evaporator side, one for condenser. And this is our compressor, how it looks like. Helical rotary air-cooled compressor, our specs are here, again, based on the way the compressor looks like. Their name, again, evaporator, condenser, are located down here as well. We also have absorption chiller that mainly the input is the thermal energy. It could be coming from the waste heat you have in a system or steam. The way they work in a simple scenario is that you are replacing your compressor in a refrigerant cycle with these three components: generator, pump, and absorber. So these three items on the right-hand side I'm showing kind of replace your compressor. Otherwise, condenser, expansion valve, and evaporator are the same. Another difference is that not only you have refrigerant, you also should add an absorbent, another material as well. Very common refrigerant absorbent is water and lithium bromide. That water works as a refrigerant, lithium bromide works as an absorbent. What happens is that a mixture of vapor coming out of the water coming out of the evaporator and lithium bromide as absorbent mix here. So absorbent is a desiccant material and that loves to absorb water. So they're mixed together, they absorb the water, and a pump instead of a compressor. So we're using much less energy, pumping the whole mixture into the generator. That's where we are receiving the heat, and refrigerant evaporates going to the condenser, and the absorbent kind of in the form of liquid go back to the absorber. So the condensed water reject the heat, goes back through the expansion valve and repeating the cycle. So this way we are absorbing heat from on the evaporator side just by providing the heat in the generator. That heat could come again from the steam or hot water. This is a more detailed single effect absorption chiller that kind of works exactly the same. You have your condenser here. Top part is your generator. This is your absorber. And this is how steam comes into the generator. This can come from exhaust gas from a furnace or a steam from a boiler if you can run the boiler at a higher pressure to get a steam out of this to run such a cycle on the side. More on other types of the system, HVAC system. This is how a chiller, electric chiller looks like. That you have a cooling water, and you have a cooling tower serving the condenser of the chiller. An evaporator has its own loop to kind of provide cooling for the building. Here we have different types of cooling towers. You can either have a forced draft towers that on the bottom side mostly we are forcing the air to go through the tower. So the water comes downward, air is going through the water. There's a direct contact between water and air that's caused evaporation. So that evaporation cool down the remaining of the water. That's the really main principle of cooling water using the cooling tower. But in a forced draft cooling tower, they are more limited, they're smaller, and you usually force the water, air from one side. Induced draft cooling tower, on the other hand, you have the fan, the motor and fan on top of the tower, and you are pulling the air through the water, and it could be open from two sides mostly. And it comes with different sizes and shapes, circular, rectangle, kind of square geometries. We also see natural draft cooling towers as well, that there's no fan involved most of the cases, and kind of naturally induced going upward. Here we're looking at the main features of cooling towers. We have to treat the water before put it into the cooling tower. So there's a makeup water because we're going to evaporate and drift. We're losing some water, so we have to always provide the makeup water after treatment. Of course, we have to blow down continuously as well, just to get rid of the unwanted, really solid materials. And there's a pump circulating the cooling tower water through the condenser and capturing the heat from the condenser of the chiller, bringing the warm water at the top of the tower, and kind of gravity pulls the water down while air, in this case, probably induced draft cooling tower, pulling the air upward, and that's how fill materials inside, let the water and air contact directly, and then evaporation happen. Kind of reviewing a fan laws, and that there are three equations on fan laws, which is very important. One is that the volume of the air varies directly with the speed ratio of the fan. So if we manage to bring the rotational speed of the fan 10%, we are decreasing the volume of the air 10%. So it's a linear relationship. In regards to pressure, it varies with the square of the speed ratio. If we manage to kind of bring it to 10%, we are decreasing the pressure 0.1 to the power of 2. And in terms of horsepower, varies with the cube of the speed ratio. So it's very important, if you are capable to bring the rotational speed of the fan lower, we are significantly saving on the power use of the motor here. One example here, kind of showing that a 10% reduction in the speed will result in 27% reduction in power. So let's look at this. Let's assume the initial RPM, rotation per minute, is 100. The 10% reduction means 90 RPM for the state 2. So 90 divided by 100, which is RPM 2 divided by RPM 1 to the power of 3 is 0.73 or 73%, which means that we reduce our power 27% just by reducing the RPM 10%. So this comes important whenever we talk about VFD on the cooling tower fan. We have a few the slides on that that I'll cover later today. In terms of HVAC, in the past, of course, it could be really controlled as simple as using a thermostat, a set point, or it could be more and more sophisticated by using a remotely accessed, computerized building management system. We can plot we can trend the data, we can analyze it, we can set alarms, we can kind of work based on the information. So building management systems comes with various options, including HVAC on top of, everything else, security, lighting, fire protection, power distribution, and you can exactly monitor your demand peaks, your behavior of the energy use, temperature, really every sensor and that can provide useful information. So in the rest of the slides, rest of the presentation, we're going to talk about on these 8 items that how we can look at the builds to kind of make sure we get most out of the energy efficiency. On building management systems, we're going to talk about commissioning, retro commissioning. We're going to talk about minimizing ventilation air, free cooling, VFD on the fan, on the condenser flow. We're going to talk about the variable refrigerant flow systems and reduce condenser water flow rate. I think we will talk about few other things as well, which is not listed perhaps here. In terms of belts, so many motors and fans are connected through the belts. One thing is that whenever we upgrade our motor from probably a standard efficiency after a while to a very high efficient one, so if you're really getting a new one, replacing it with the newest one, of course, we're gaining some efficiency. For example, in the 50 horsepower motor, we can go from 91.4 standard efficiency to 94.5. So we gain some efficiency, which kind of gives us reduction in power use because motor works more efficient in the same condition. Let's assume it works all the time in a year for an 8 cent per kilowatt hour cost of electricity, a blank cost. We're talking about saving about $939 per year just by upgrading a motor from standard to a more efficient. On the other hand, another option would be rewinding. So if it breaks down, we can have it rewind. Of course, probably we're going to lose some efficiency, some points. So I guess one study could be, is this worth to lose some point of efficiency and in case we're using it that long, or be better off upgrading to a better efficient motor and kind of save energy that way. And sometimes whenever we do the rewind, we're gonna make sure that the efficiency is measured, so it's not too bad. And of course, with the more efficient motors, we might get a faster rotational speed. So in some application, I mean, it might be good, but it looks like we are faster speed means more energy use. So we have to be careful of that as well. In terms of belts, there are a lot of V-belt that we typically suggest to go with the cogged V-belt or synchronous belts instead of a standard belt. We did some study at Tech. We collected some experimental data as well. And there are literature outside. We can gain 2% for a cogged V-belt, up to 5% for a synchronous belt by just changing the belt from V to, let's say, cogged V-belts or synchronous V-belt, whenever we need to change them when they're out of working condition. So, for example, for a 100 horsepower motor that kind of works at 80% load, that would work. That would use 62.8 kW. Let's assume they have a standard V-belt. The amount of energy use is 550,000 kWh per year. For the 8 cent per kilowatt hour, that means $44,000 a year, $44,000 a year. Changing to cogged V-belt would save 11,000 kWh per year. We're talking about $880 saving per year. And of course, if you change it to a synchronous belt, your saving is more, but synchronous belt do not slip because they really goes on those threads, as you can see. And then if the motor are on and off all the time, it's not continuously smoothly running, it might cause some problem or maybe loud noise. So again, based on the application, it could be picked according to the application. Here, I guess we're listing building automation systems for building management system for HVAC systems, and they can control and do a lot of things, controlling outdoor air intake, maintaining temperature set point, so they can do free cooling cycle. They can really control the system. Let's go to the details of some of those, and they can trend the data as we said earlier. Commissioning retro commissioning is important. The goal is to make sure the HVAC design for the system is working based on the kind of design condition and a standard control sequence. Not one approach works for all systems, so we have to make sure for the application that HVAC system is installed, the approach is working perfectly. Typically, regular retro commissioning leads to a 15 to 20% saving in energy associated with the space conditioning. Again, it's not a one-time deal, so you have to control it and regularly have it checked. ASHRAE standard talks about minimizing the ventilation air that in a heating and cooling load calculation, the introduction of indoor air, outdoor air is expensive. So that means that we have to do some cooling or heating on the fresh air coming out from outside. And you have to make sure we're following the ASHRAE guidelines to calculate based on the minimum ventilation air. There are tables that you can say, okay, for an example of office space, we need 5 CFM per person, and depending on how many person you're using any design condition for that room, and then we can add based on the square foot CFM, so you can design your CFM based on the kind of provided tables. Again, conditioning ventilation air is expensive. Fresh coming outside from out, cold in winter, hot and humid in summer. So we can use different methods to reduce the amount of outdoor air, or it could be based on the occupancy of the space, which we call it demand controlled ventilation. So you might use a carbon dioxide sensor that based on the required carbon dioxide inside the room, we can control the ventilation, or it could be based on the occupancy sensor, depending on the number of people, or a scheduling based on the time that pre-scheduled from the, let's say for a week. Here we're talking about indoor air quality, which especially with the current pandemic we are in, it might be more related. So indoor air quality talks about concerning about inside of the building and around the building. Air quality can relate to any particulate in a building or a space. It could come from a smoke. It could be coming from the cleaners and detergent particles coming from the cleaning side, from mold, from poor circulation. Study shows that relative humidity has a direct impact on the occupant health, and the sweet spot for relative humidity is around 40 to 60% relative humidity, where usually growth of viruses, bacteria, other particles are almost minimized in this range. And poor ventilation, poor air distribution makes it even worse. So we have to make sure that our ventilation system, the humidity level are exactly controlled. One way to kind of start tackling this is that making sure we are measuring the content using different sensors. We can have carbon dioxide sensor, radon, humidity sensor, temperatures, particulates in the air, so VOC sensors that kind of making sure we have a ppm, particle per million content of any particles we can see, and there are sensors that we can track those and kind of work based on those. One of the equipment used a lot recently in the last year was bipolar ionization. That we have an ASHRAE meeting about a month ago that they talked about this. It's a popular equipment people using right now that to control the viruses, bacteria. That what happened is that ions naturally aid in particulate removal. So what happened is that they take a molecule of oxygen, O2, and they split it into a positive, negative atoms of oxygen. And when they react with water, hydrogen peroxide is formed. And that hydrogen peroxide, with the help of water molecules, they go around the harmful particle, let's say virus, and kind of do a chemical reaction. And the oxygen breaks down the pollutant. And this is how it works. Another solution is bringing more outside air, fresh air, just for the purpose of the health. That you can really bring the fresh air is also recommended by ASHRAE. That in the case of kind of condition needed, especially for health conditions, we can bring fresh outside air into the building. We have a dedicated air. Other approaches are making sure we're using humidifier or dehumidifier to control the humidity. UV light are also has been used greatly for removing particles as well. One downside with UV lights is that you have to replace the light every almost 9,000 hours of operation almost every year, but it works great. Filtration is another important thing. You want to make sure your filters are regularly changed. The MERV number, MERV stands for Minimum Efficiency Reporting Value. 13 is used for hospitals, so medical grade. It's not, probably cannot be found in like a stores for building or residential use, but MERV of 4, 6, 8 are totally fine as long as we kind of change them regularly. Every 3 months would be an idea. So on top of that, we have to react. We have to make sure our sensors are working. Humidity level was the key, carbon dioxide, VOC sensors. Changing the filters, 30 to 60 days. So I take my words back, 3 months. It's like every 1 to 2 months. And we can invest more on sensors, especially making sure that in offices or indoor, we know in terms of ppm of particles, humidity, where we are. There might be roadblocks. We have dealing with all equipments which are not connected to BMS systems, or there might not be enough room on the floor, on the roof, or the equipment are expensive. There's no budget. So as long as we can identify the roadblocks and kind of plan around those and make sure we can find a solution. If we understand the problems, it's easier to find a solution, so we can go from there. There might be incentives from the energy providers as well, so you need to always check with utilities as well. Over here, we would like to talk about free cooling. I just want to check, make sure everybody can hear me well and everything is going well. Is there can someone confirm?
Yeah.
Yes.
Awesome.
Still anchoring.
Okay. Awesome. This is great. Over here, we're talking about free cooling. We're going to focus on air side economizer, free cooling with plate and frame heat exchangers for chillers, and free cooling chiller as well. So this is a kind of pretty long text that probably you went through this if you had the slides in the past. But the summary is this: that imagine you are in a kitchen and the weather is a nice fall day outside. You're baking a pie, and outdoor air is perfect for breathing Would you like to open the windows and enjoy the fresh air? And the answer is of course, because if I can turn off my AC and outside air is perfect, why not? So the same thing works with kind of air conditioning. If the dry bulb and wet bulb temperature permits, if the relative humidity is not too bad, why not using the free fresh air from outside? The map you see on the right-hand side shows the airside economizers hours. Of course, this is for data centers, but for the US, that kind of shows the number of hours available that dry bulb and wet bulb temperature are below certain points. As you go from south to north, that number increases. So you can use more free cool air from outside as you go toward the north in the US. So one system is using an enthalpy sensor that kind of measure the outside air enthalpy and the return air enthalpy, and based on the information, if the outside air is cool enough, and of course enthalpy consider the humidity content as well. So really what happened is that we stop using the compressor, the condenser, the fresh air from outside goes directly to the supply, or a mixture of return air and outside air. So this way we can save energy. So in this case, outside air comes in and directly goes to space. And of course, we're blocking this way because we're not using the compressor. So by comparing the enthalpy of return air to the enthalpy of the outside air and maximizing the use of less energetic stream. Here is a plot showing that usually we have a 20% outdoor air mixed with 80% return air. But at some point, outdoor air is nice enough so we can increase the use of outdoor air and decrease the use of return air, all the way until we can get maximum use out of outdoor air. In this case, 100%, all the heat, all the air coming from outside, 0 from return. And of course, we're limited. We're kind of hitting the limit on the right-hand side, and we can go back to norm. The painted area in black shows the amount of energy saved because we use the outdoor air in the form of airside economizer control. We can talk about plate and frame heat exchanger on the water side of the chillers when we do a free cooling. So here, what we have is a chiller serving a building, and it rejects the heat using a cooling tower. Now, let's assume if it's cold enough outside, that cooling tower can provide cool enough water that serve the building. So we don't need to run the chiller. What happens is that we can turn off the chiller. In this case, there is a plate and frame heat exchanger, as you can see in a red block, that the loop of the building load kind of interact and exchange the heat with the tower loop, to separate loop, making sure this loop is not exposed to oxygen. So this way we are shortcutting the chiller, the cooling tower, just serving the whole building for that period of time when we can get enough cold water out of the cooling tower. One example of this case is that let's assume we have a 500-ton chiller at the COP of 0.6 kW per ton, which if you multiply that with the 500, we get 300 kW electrical load on the chiller. Let's assume the 1300 GPM we have for chilled water flow, and we have on the condenser water flow, we have 1500 GPM. For the cooling tower, the fan is 40 horsepower, about 30 kW. If the ambient condition is 45 dry bulb and 38 wet bulb, let's assume the approach of the cooling tower is 8. Approach is the difference of the exit water temperature of the cooling tower from the wet bulb temperature. So 8 degree F above the minimum we could achieve ideally, which is a wet bulb. And let's assume our heat exchanger's approach is also 2 degrees. So 38 wet valve plus another 8 from the approach of the cooling tower plus another 2, that gives us 48 water, which is enough to be used for the building. So as long as we have that 38 Fahrenheit, we can provide a free cooling to the building without using the chiller, which means that instead of running 300 kW, we only run 30 kW for the fan of the tower. We're talking about saving 270 kW of power for a 7 cents per kWh, for example. We can save $18.9 every hour. We can also have another form of free cooling inside the chiller. That's when, again, the cooling tower provides enough cool water on the condenser side that we can use that as the kind of source of the cooling. And what happened is that we can use a thermophone free cooling. And in this case, what happened is that in a regular case, we have the compressor working on the chiller to reject the heat on the condenser side. And of course, we repeat the cycle. On this free cooling mode, we turn off the compressor, we shortcut the compressor, and then the vapor, when it evaporates, when it boils, but naturally goes toward the colder area, which this slide, you're bringing the cooling tower water, you cool it down, makes it heavier, condensed, and by gravity goes back to the evaporator and repeat the cycle. You can get up to 60% of the capacity of a really full load cycle of the chiller by turning off your chiller and just using this free cooling benefits. Now, I guess we're switching to pumps and fans from the chiller. We're going to talk about VFDs, variable frequency drive on pumps and fans. We can do different speed controls on pumps and fans based on the capacity. That is much more efficient than throttling the valve, as you can see on this case, and discharge damper or discharge dampers. So what happened is that in most of the time, or many cases, the pump is oversized for the system, so you end up with a lot of flow rate that you don't need. So you use a throttling graph to throttle the valve and kind of control the flow rate. You don't need that much water or that much air, so you throttle it, let's say 30%. What happens is that you're providing a lot of pressure drop across the valve. What happened, the motor is working as hard, but you're just minimizing the control. There are different ways to control the flow rate. You can have an inlet damper, inlet vane, or outlet damper, which that causing a lot of extra pressure, which resulted in an extra head. So imagine we are operating at 100% speed, this black line, and this is our system with the throttle valve. What we can do, we can open the valve all the way, so there's no throttle valve anymore, but using a VFD to reduce the speed of the motor down, let's say to up to 70%, at the same time, we are maintaining our flow rate of water, our fan in this case, and then let's see how much we are dropping in terms of head, which is directly related to the energy use. So we're going from 110 head all the way down to 45, let's say, by reducing the rotational speed using a VSD, variable speed drive, and kind of bringing the head down. Here we have an example that from one of the assessments, the condenser water loop was, and the pump was too big for the system. So they had two valves in front of the flow. So one valve was located at the condenser exit, another valve at the pump discharge, both about 30% open. So we're talking about going from here to providing this much flow rate, let's say 1700, by opening the valve, reducing the pressure drop by using a VFD and bringing the head down all the way to 50 from 130, let's say, or 120. Again, opening the throttle valve, but using VFD to bring it down. Quick example on this. If the efficiency of the pump is 75%, 95% efficiency for the motor, for a 1780 gallon per minute example we had here. For the 63 feet of saving head from 100, let's say 15, all the way down to around 52. And then a specific gravity of water, you get 28.3 horsepower saving, which you can transfer to kWh, to transfer to power in kW, and operation hours a year, 8,000 hours operation, 6 cents per kW. We're talking about around 40,000 saving a year. The cost for a VFD, roughly $200 per horsepower, having it installed, is around 15,000. So in about a year, it pays for itself. So a simple payback period is around 1 year. So depending on the way we control the flow, the savings are different. So if a fan is operating at a 60% capacity, note the difference in energy consumption depending on the type of technology used in controlling the fan. So VSD is the variable speed drive, is the most efficient one. You see this dark line down here, using the less power required in the form of percent. This line is the outlet damper, which is the worst case condition for this, let's say for the 60% nominal flow. You're going from 20, let's say 5% using VSD all the way high to around 78%, let's say for the for this outlet damper. So the way we control the flow is significantly impacting the power use by the motor. Here's another example from one of the assessments that here's a boiler combustion air fan, 75 horsepower combustion air fan. It was controlled with an inlet guide vane. And here we collected measured data that in the case of inlet guide vane control, the fan power use is this blue line. While after they changed to VFD, they measured the power use, and you see how much lower it is, especially at the lower RPM or lower airflow CFM. Here they collected some measured data that they divided those CFM based on hours, based on percent in time, and compared the kW used in terms of VFD or damper control, and they showed that they saw 1.6 years simple payback period, that in less than 2 years it pays for itself for the cost of the installation. Now we're switching to, I make sure it's 10 minutes to 10. Now we're switching to heat pump water heaters that kind of utilize the heat pump loop, which we talked about. You have a compressor, condenser, evaporator, and expansion valve. So instead of rejecting the heat from the condenser to water or ambient air, the outside unit we have in our building, let's reject that heat into a tank of water and bringing the cool water of the kind of indoor space where this water heater is installed to cool inside, let's say, a garage in a residential application or a facility. And so you're cooling your inside air while you're adding the heat using this heat pump to the water heater. So components are really typical components for heat pumps. You have a compressor, evaporator, fan on top. You have an inlet and outlet for water, you have a drain system, typical water heater, and you always usually have a resistance element for the cases that the demand is high. So operation-wise, exactly the top part works like a heat pump. A fan pulls the air from upper enclosure. Air goes through the filter, and then heat of the air is gained by the refrigerant inside the evaporator coil, and cool, dehumidified air is exhausted to the space. So this way you cool down your space, great for summer really application. Refrigerant is pumped by a compressor similar to heat pump. Then you increasing temperature, refrigerant delivers to the condenser, which goes around the water tank, wrapped around it, and heat is transferred from the refrigerant to the water. Efficiency-wise, and they pay back for themselves for, depending on the size. We couldn't find really other information than this small sizes of household, but usually pays for itself for, let's say, from 2 years to 4 years. In this side, in this section, we're going to talk about VRF systems, variable refrigerant flow systems. So I have several slides on this, but first I'll make sure I define those correctly and in details. A VRF system is a direct expansion air conditioning system that connects multiple indoor units to the same refrigerant system. So you have the same refrigerant system, but you can provide, you can connect those to multiple outlets. So there are 3 types of VRF system. We're going to talk about all those types. One type is the only cooling system. So that type only provides cooling. The other type is heat pump system, like we have, that can provide cooling and heating. And the third part, which is kind of unique to this VRF system, is that heat recovery system. You can provide heating and cooling at the same time, which is kind of unique to this VRF system. Let's go through more details over here. Components-wise, they have outdoor units, heat recovery control unit, indoor units control refrigeration piping. Outdoor units typically contains 1 or more compressor. In case of more compressor, usually you have a VFD one and you have few base ones. Because there are multiple indoor units with varying loads, most units contain multiple compressor. They call it variable refrigerant flow because they refer to the ability to vary the amount of refrigerant that flows through the system. So based on the load of the cooling in each separate space, rooms, you can control the rate of refrigerant going to that room. Outdoor unit also contain a heat exchanger that serve as a condenser in the cooling mode and evaporator in the heating mode. An additional heat exchanger or intercooler is provided to increase subcooling in the cooling mode and heating in the heating mode. The fan may be fixed speed or variable speed in the heat rejection side. Expansion devices provided to lower the refrigerant pressure before the outdoor coil when operating in the heating mode, and then there might be an oil separator as well. Here, in terms of operation, during the cooling operation, let's assume we only first type, they only provide cooling. Hot, high pressure refrigerant compressed in the outdoor unit where there's a compressor and goes to the heat exchanger, which serves as the condenser, rejecting the heat. The liquid refrigerant is then distributed in the indoor. During the heating operation, heat pump, VRF system, reverse the cycle, typical system, and provide the heating. In this mode, the heat exchanger in the outdoor unit serves as the evaporator. So far has been similar to typical heat pump, but here we're controlling the refrigerant. Heat pump VRF systems can provide either cooling or heating, but not both at the same time. That's type 2. We're not even we're not still at type 3. If one space receive cooling, then all the space will receive cooling. And same thing with heating. You can either heat or cool, but you can kind of control, adjust the flow rate of the refrigerant. But the third type, this is the unique type that kind of more unique to this case, that the heat recovery VRF system have the ability to provide simultaneous heating and cooling because both hot gas, pressure gas, and cold liquid refrigerant are available to indoor units. So this is the unique part. So heat recovery control module, HRCM, enables the system to provide both cooling and heating. Imagine you have a conference room that needs cooling because there are a lot of people in that, and in the same building, there are other rooms that is too cold, needs heating. So the same system can provide cooling and heating to two different spaces. The control unit acts like a traffic police and that able to direct either the hot gas or cold liquid to the right place. This requires a sophisticated control. So this is how it works in a kind of simple cartoon shape that depending on the cooling and heating needs, the HRCM control box decide to take the hot gas from one side and directly send it to the other side, even without sending it back to the compressor. Same thing with cooling side, and of course it has its own connection with the outdoor unit to make sure it has enough refrigerant at various really conditions ready. So the HRCM is able to route cold liquid refrigerant to the indoor units needing the cooling while sending hot gas to the other units needing the heating. Also can route refrigerant from one indoor unit to another indoor unit directly. So this way you're saving significant energy on the compressor side. This works by transferring energy between the indoor unit that are working in the opposite nodes. So this is how they look. They don't need a lot of ducting. In many cases, they are ductless, and each contain a coil and expansion valve. Some models are designed to fit into a small closet. Other units require a small section of a duct to discharge air. Some cases, they can be controlled easily. They have a controller, looks like a TV controller, or in the case of duct one, they are wired remote connections. Indoor units, let's look at those. Small buildings with a single VRF system, usually ductless, utilize a wireless remote. We talked about it. They offer on-off operating mode, temperature set point, fan speed. You may be able to use connect one to multiple control systems using one remote. For the duct one, we talked about it. They're wired. A wireless remote controls could be used with the ductless indoor unit if a remote wireless signal receiver is installed. For a larger building with several individual VRF systems, a VRF controller can be used. So they have a good control that allows to integrate with the BMS system, with the rest of the equipment. On a cool March morning, let's read this together. On a cool March morning, when people arrive at work, consider this scenario that they will generally needing heat to counter the nighttime building cool down. So the system goes into a heating mode initially and satisfy the occupant heating. Later in the day, the occupants in a conference room needs cooling, but rest of the building probably needs heating. So this system can satisfy multiple needs, which is really, we talked about it earlier. So the solution is to specify this system as a heat recovery system capable of supplying either heating or cooling to any zone at any time, while a heat recovery control unit is needed for this purpose that can provide both of them at the same time. So I guess I'm going to skip you off those details of the control system. You have a discharge gas line, liquid refrigerant line, compressor, suction gas line that kind of helps you control. We talked about those. That works for simultaneous heating and cooling. I leave those really for your reading for further details. Really step to step how they work. But let's take a look at this in terms of energy saving using those variable refrigerant flow. US DOE estimated the average energy use in a commercial building that look at this graph, that refrigeration and equipment, lighting, cooling and heating, and ventilation. If we combine these cooling, heating, ventilation, that's what we're talking today mostly. We're talking about 3 plus 2 plus 2, 7 kW per square foot. I would assume this is for a year annual energy use. That's the amount of heating, cooling, and ventilation that is required. For example, for a 30,000 square foot office building, using this 7 kWh per square foot in a year gives us 210,000 kWh per year, 8 cents per kilowatt hour estimation. We're talking about $16,800 per year. With conventional HVAC rooftop units, and if they provide 30,000 CFM with such a static pressure of 0.7 inches of water, fan energy would be about 3.8 kW or 33,000 kWh per year, or 1.1 kWh per square foot. This is 15.7% of the total with heat recovery VRF. That could save you 25% to 40%. So for if you have such application that you might need to kind of control the heating, cooling at the same time, or controlling even just heating or just cooling, but at multiple loads, VRF system can save you really significant amount of energy. Here, now we're switching to variable speed control for cooling towers. Let's take a look at the control system on cooling towers. In the past, controls were much simpler. Energy was cheap, so we didn't worry too much about those. And typically, the rule of thumb was that depending number of chillers you should have that same number of cooling towers to serve those chillers. But in today's life, controls are much more complicated. Energy is not as cheap. So really, we're trying to see, are there any other ways to save energy by optimizing the operation of the cooling towers? Same thing we talked about, the fan affinity laws. Same thing, of course, applies here on the fan of the cooling towers. So cooling towers capacity varies directly with the fan speed. So 100% speed, 100% performance. 75% speed provides 75% capacity performance. So they're related directly. But as you remember, on the fan energy use, they vary with the cube of the speed ratio. So if we can bring the RPM, the speed of the fan, 50%, 0.5 to the power of 3, we are talking about reducing the power use from 100% to 12.5%. This is how the fan energy varies. Now let's take a look at few scenarios that, let's assume this is a traditional setup. We have a 3,000-ton chiller plant, which composed of 4 chillers, each of them 750 tons. And there are 4 cooling towers, 4 cells of towers serving these 4 chillers. So here are my 4 cooling towers, 9,000 GPM. 95, 85, 78, those are my conditions of the tower, design condition. Let's say each tower is 40 horsepower on the fan. So what happened is that if I use 70% of the load, so let's assume 3 chillers working at the same time, 1 chiller is off. In an old way, 3 chillers mean let's turn off one of the towers, let's turn on the other 3 towers. So this way we kind of provide servicing our chiller. So 3 fans, each 40 horsepower, 1 is off, so total is 120 horsepower energy use. So end result is that if you're running at a 75%, then 75% load with the traditional approach. Now, let's say for the same chiller load, so 3 chillers out of 4 chillers working, but instead of just running 3 towers, let's use all 4 towers, but at the lower speed. So in order to serve the chiller, we have to bring it down 75%. So this way our total GPM is equal to the incoming gallon per minute flow rate of the condenser flow. So now because we reduced 75%, our power, as you remember, varies with the cube of the reduction speed. So instead of 40 horsepower, we are talking about 16.9 horsepower for each fan. So 4 fans work at the same time, total is 67.6. Remember, it was 120, but we can provide the same chiller size, 75% with much lower horsepower. So we're talking about 44% energy saving compared to just kind of more traditional way of having 1 off. Now let's assume another scenario. Our chiller plant is 50% load, which means that 2 chillers work, 2 chillers is off. Now let's distribute all the condenser water flow between the 4. Now we're reducing the speed to 50%. Again, the power use is the cube of the reduction in speed. So our 40 horsepower fan just worked 5 horsepower, and the total of 4 will be 20 horsepower. And we're talking about 75% reduction in energy use because we are using all of our towers, but because of using VFD, we can reduce the speed down. That was it. But yes, there are limits on how low you can go. So you have to check with the specs of the cooling tower. So you may not, maybe in some cases, go as low as 30%. So in that case, you have to turn off one of the towers and meet the minimum reduction in speed. But still, in this case, that we're just having 1 chiller on, 3 chillers off, still we can use this concept, 1 chiller, 1 cooling tower off, but 3 cooling towers serving, and then really we're talking about 4.5 horsepower out of 40 horsepower or 88% energy saving. So the way you control the multiple towers, if they're connected to your chiller plant, is very important. Make sure that's why VFD opportunity is great for controlling the kind of VFD fans. We can also talk about if VFD provides any benefits to the condenser water flow as well. So assume this is your cooling tower, and you're serving your condenser chiller water. Now the question is, do we like to have a VFD on the pump kind of pushing the condenser water or not? Or should we vary dynamically the condenser flow or not? So really the answer is yes and no. If you're talking about savings are available, if the system is pretty old, because older systems were designed for 2.5 to 3.2 gallon per minute per ton, which really providing a delta T of 12 to 9.4 Fahrenheit condenser water flow rate. So if the system is really the older system, there might be opportunities, but in the new system, they designed already based on 1.8 to 2.2 gallon per minute per ton to providing this 16 to 13 delta T for the condenser water flow. And they already achieved the optimized condition. So there are not much if you are using a kind of more recent loop using VFD on the condenser water flow. There's been a study that we can take a look on this slide, 10:15. So it looks like I have around 30 more minutes or so, or less than that. Let's take a look at this variable condenser water flow table. Here, first row shows us the baseline. Let's assume we have a chiller type with a variable speed. A cooling tower, they have the option to be variable speed. Condenser water flow rate is around 3 gallon per minute per ton. If I go to the previous slide, 3 is on the kind of larger GPM per ton, kind of older system I was talking about. And condenser water flow rate is a constant flow. Power control method is kind of optimum condition based on the way they talk about it. So all of them are optimum. kWh per ton, and of course this is the baseline, so no saving applied to our baseline. But let's assume we have a variable control, variable condenser water flow. The only change here is that our condenser water flow is variable flow instead of constant flow. Now you can see that you can save up to 3.7% by using a variable VFD on the condenser water flow, especially for this high GPM per ton, which is the older design. But let's see if we have the reduced design condenser water flow, which is 2 gallon per minute per ton, which if I go to the previous slide, this is around the range of a more modern one. Then itself, it gives you 3.8%, even without using VFD on the condenser water flow. You can see that it gives you 3.8% enhancement compared to the baseline. But on the last one, you see that for the same 2 gallon per minute per ton, even if you use the variable frequency drive on the condenser water flow, your saving is the same. So no benefit in adding variable frequency drive VFD on the condenser water flow if your design is more recent or your GPM per ton is around 2. So it's already optimized. Okay, this table is talking about that. I'm gonna keep going forward, talking about desiccant dehumidification, another way to kind of dehumidify, getting a humidification, moisture out of the air, helping the cooling system. So what happens is that usually a damp air, moist air goes through the desiccant wheel, which rotates slowly, and dry air kind of leaves the desiccant dryer, let's say, and we have to use another section of the wheel to push the hot air, dry air to regenerate, to kind of get rid of the moisture collected in the wheel. So desiccant materials absorb water vapor from the air. So the water stick to the material. In the HVAC industry, there are 3 common types of desiccant, and they categorize based on type 1, type 2, type 3, based on their ability to hold water vapor at 75 degree across 0 all the way to 100% humidity, relative humidity. So let's look at this on this chart. That horizontal axis goes from 0% all the way to saturated 100% relative humidity, and vertical axis talks about the ability of the material to hold water vapor at 75 degree dry bulb temperature. So you can see that type 1 desiccant are pretty good at the low relative humidity. They can absorb it well, but going from 40 relative humidity, 40% to 100, it remains the same. On the other hand, type 2 is lower on the initial relative humidity, but it's much higher than type 1 at the higher relative humidity percent. Type 3 is not as good compared to type 1 and 2 for the first, let's say, I don't know, 80% relative humidity, but at higher relative humidity condition, it works the best. So you get maximum ability to hold water vapor at worst case scenario, 100% saturated condition. So the way they work is that, so the wheel or the solid desiccant dehumidification wheel slowly spins, so 10 to 30 rotation every hour, so very slowly rotating. The absorption and regeneration process are driven by difference in the relative humidity of the respective air streams. So dry air comes in, drop the moisture, and moist air gets dry and leave the wheel. Here we have a few cases that using the desiccant type 1 and type 2 we talked about. This dedicated regeneration system that includes the heater in order to lower the relative humidity, cooling coil downstream of the dehumidification on the wheel. So let's take a look at this. This is our wheel, desiccant dehumidification wheel. So what happened is that RG, the air comes going through the heater. So you are going through the heating, you're adding the temperature on a psychrometric chart starting from this point, 87 dry bulb and 130 grain per pound, your humidity, specific humidity. You go to the right-hand side because you're adding your temperature, but you're not reducing or increasing your moisture content. So your moisture content remains the same, but you're going to RG prime. And you go through the desiccant wheel, which means that you are gaining a lot of moisture from the wheel. So your moisture content goes up and you cool down a little bit because you're going through the wheel. So you're getting the moisture out of the wheel and making the desiccant wheel dry. So you regenerated the wheel. Let's take a look from the outdoor air coming into the wheel at the same temperature, and gets drier by going through the wheel. So it gets drier, which means that we're going from OA all the way to OA prime. It goes down on this vertical axis because you're losing moisture, giving it to the wheel. But because we heated the kind of wheel, we are gaining some temperature as well in the air. That's why we need to do some cooling before dumping the air into the space. So we provide some cooling. We're not condensing any water. So that's why we are just going along the constant specific humidity all the way to CA, which goes into the room. So this is how it works on the side chart. The traditional arrangement problem is that you have to heat it and you have to cool it. Let's quickly read it. Heater requires additional energy and adds considerable sensible load on the system. Conditioned air is usually neutral or even warmer. Cooling coil is more effective when wet. So the same process we talked about. This is a traditional way. Now in the next slide, we talk about what if we bring the cooling on the other side, because cooling coil is more effective when they're wet. So if you bring the cooling on the other side, what happens is that starting from RG, which is the outdoor air, going through the heater, we heat up our air, going to RG prime at a constant specific humidity. Going through the wheel, we're adding moisture to the air because we're collecting the moisture out of the wheel. So it goes up, it gets a little bit cooler. On the other hand, outdoor air first cool down, unlike the traditional way that first we push it through the wheel and then cool down. In this case, in the in the newer kind of model, first we cool it down, and we may condense some water. So as you can see, we go from outdoor air and cooling it down mechanically over here. We go through the saturation line, 100% relative humidity, all the way to CA, where we are losing humidity because we're condensing. At the same time, we're going to the left-hand side of this axis, which means that we're cooling it down. And then we do an additional moisture removal by going through the wheel, which that's where we go from CA to CA prime. That we're gaining some heat because we added heat to the wheel at this point. So, and then we are still losing some humidity. So this is great in terms of combining our desiccant wheel with the cooling process, but cooling on the left-hand side. And we can have another form, which is a series regeneration, remove the separate regeneration airstream, eliminate the need for the heater. So there's no need for the heater in this case. For the heater, the difference in the relative humidity is driven completely by the cooling coil. And you can use the type 3 desiccant in this case. Conditioned air is capable of cooling. So what happened in type 3, you can use it in series, which means that you put the outdoor air through the desiccant wheel. So you gain some humidity out of the wheel. So you go along the humidity increase. And of course, you're losing some temperature going to the left-hand side. And you're cooling it down all the way on the 100% relative humidity. You condense it, that's why you're coming down as you go through the cooling coil. And at the point CA, you go through the wheel one more time, you dry more, that's why you come down in terms of a specific humidity, but you gain some heat. That's what we provide to the space. So less heating on this side, and we save some heating kind of cost in this case. This plot kind of represents the 1025. I'm just checking, make sure I'm not going over the time. So this chart table compare the parallel configuration versus the series one, which I talked about the last. We will see that in the series, we don't do the heating, but we need to provide more cooling. And on the cooling capacity, it's a little bit less than parallel configuration. And overall, the total cooling capacity for the same when we compare those together. So no regeneration, heat required for the series, added cooling capacity at the dedicated outdoor air unit helps offset the space cooling load, enabling smaller local HVAC terminals. So this is what happened. Let's assume an example of a mixed air. So we have a series regeneration can be used in the mixed air stream because the supply air is cold enough to use the conditioned airspace. So let's assume we're bringing some return air and mix it with some outdoor air. So on a side chart, we typically connect those, and then depending on the mass flow rates of return air and mass flow rates of the outdoor air, we meet somewhere in between. That's going to be the mixed air. The use of the return air and possibly a reheat allows an even lower dew point to be used. So what happened is we go from the mixed air through the wheel. That means that we're gaining some moisture by going from MA to MA prime by going through the wheel. And then we are making it a little bit cooler. And then we're going through the cooling coil. So we're cooling it down. We go on this 100% relative humidity. We condense as we go on through the cooling coil. As you can see, we're coming down on the specific humidity ratio. And then at the point CA, we can go through the wheel. That's how we do it with the desiccant wheel. We lose more moisture out of it, but we gain some heat. because we did some preheating, or even the desiccant wheel is warmer even without preheating, and we kind of provide the heat to a space. In a traditional way, what we do is that we go from MA, from the mixed air, we cool it down to come to the desired moisture content, and then we have to heat it up using a heater to kind of provide heating, to provide the supply air at the right temperature. So the gray line kind of shows you more traditional or without a desiccant wheel. The red lines are the desiccant process. Here is an example with some numbers of the same process we just talked about. Here, let's assume we have a 10,000 CFM mixed air, 4,000 coming from the outdoor, another 6,000 coming from the return air. Outdoor are at 100 Fahrenheit and 85 grain per pound. Return air is 62 Fahrenheit, 42 grain per pound. So you calculate the mixed air on the enthalpy, on the psychrometric chart. Those are the enthalpy you get and the temperature and humidity. And here is the information from the coil discharge with the enthalpy by using your final condition. And mixed air, you can estimate the cooling required 45 tons. Let's assume the COP is 0.6 kW per ton. We're talking about 27 kW, 8-cent electricity costs per kWh. We are talking about $1,000, 577 per month. And we also need to heat it in a conventional system because we dropping the moisture down to the desired level. Now we heat it to a desired temperature before we put it into space. So we're talking about by finding the difference of enthalpy multiplying by a mass flow rate. We are talking about 150,200 BTU per hour, 80% for the burning efficiency, $6 per MMBTU of a gas. We're talking about $657 per month for just for the heating. Total cost $2,234 per month. But if you use a desiccant wheel, those are the conditions for the regen exit air. This is the enthalpy, temperature, and the humidity for the coil discharge and the four final conditions. So for this, we don't need the heating, but we need the cooling. 34 ton of cooling, if you calculate it. Again, mass flow rate times the delta enthalpy between the regen exit and the final condition. Same 8 cents per kWh. We get $1,000, almost $200 per month. No heating. The total cost is $1,190 per month. Compared to this $2,000, we are saving $1,045 every month by kind of using the desiccant wheel. So that was a quick example of that. Here, they're talking about the total energy enthalpy wheel. And so most basically, enthalpy wheels work under the same principal condition as desiccant wheel, but they're used to transfer sensible as well as latent heat. So exhaust air can be used to lower the relative humidity of the outside air. This can be very useful for preconditioning outside air before it reaches the desiccant wheel. Sometimes the energy saving are drastic enough that it could warrant downsizing the heating equipment or heating and cooling equipment. So what happened is that you're bringing your outdoor air through the wheel first, and then through the additional wheel for, as we talked about in the previous cycle. So we call those, so this first part bringing down the sensible portion of the heat, and second part works with the moisture removal on the latent heat, so your saving is significantly more. whether it will be for a dedicated outdoor air system or mixed system. If dehumidification is a important desiccant bills, they can often be used to great effect in place of increasing mechanical cooling. So those are extremely useful if the moisture content is high for the condition of air conditioning. Really, this is my last slide. I have a few equations that useful in HVAC formula, and we did 2 examples. I'm not going to go through those really, but they're examples of kind of calculating the sensible heat removal. If you know your delta T, you know your CFM, and the last example is using those equations to calculate the total sensible and latent portion of the heat. With that, I'm going to stop and I turn it to Tim and you guys to answer, to ask any question you might have or having conversation. Back to you guys.
Okay, guys, we got any questions, comments? Please jump in. Okay, well, I made a couple of notes on things that I just wanted to mention, just a few hit and miss items. In talking about the makeup water to the cooling tower, a lot of times people are paying sewer fees on that. And it's possible, depending on negotiations with your water supplier, to meter the cooling tower makeup water. And if you can prove that that water is evaporated, then you can go back to the water utility and say, hey, I need a credit back on these sewer fees. And so, you know, if you got big cooling towers, that can be a substantial amount of money. I know I think we were looking at Kellogg in Memphis 4 or 5 years ago, and it seemed like it was, I don't know, 30,000 a year or something like that. I forget the exact number, but I mean, it was certainly worth going after. So that's one thing I want to throw out there. Also, on the premium efficiency motor idea replacement, you know, this rewinding, and of course, rewinding wasn't really a topic here much, we brushed on it, but it's a real good idea to ask for efficiency testing if you send motors out for rewind, because I mean, it's quite possible if you have a good rewind shop that you'll get an equivalent efficiency back that the motor is capable of. But it's also possible to have efficiency deteriorate. And so, you know, if you have an older motor that wasn't all that efficient to start with, and then it's been rewound a couple of times, and the shop is not just doing the best of jobs, I mean, it works when it comes back, it's hard to do that testing for yourself. So if the shop has a dynamometer, then they can do that testing, and you can put that in your spec so that you're assured that at least you're not losing efficiency points on rewind. And just one comment on the VRF savings. I have a relative and works in Seattle in the HVAC industry. He works for a big mechanical contractor, and he's a foreman for them. And all they do is VRF systems. And they do a lot of retrofits on like large apartment complexes and things like that. And they often write into their proposals that they will guarantee a 30–35% energy reduction as part of the retrofit. And his guy's name's Rick, and I was talking to him. I said, Rick, man, that's a lot of savings. Do you have problems reaching it? And he says, no, we never have any problems reaching it. So this VRF has been big in Europe and Japan for probably 15–20 years or longer. And it's just been the last probably 10 years that it's made it to the States. But VRF, because of the, the fan requirements are very minimal. I mean, you got to have a fan to blow some air, but it's compared to a large central station air handler where you have, significant static pressures and fairly large flows. The fan energy reduction is very significant. That's why that example calculated for that 30,000 square foot building about 15% or something of the building heating cooling energy would be assumed to go into fan energy. that VRF is going to have very, very little of that. So you wouldn't get all of it. I mean, you still have to move some air, but maybe you would get 10% or something like that savings off the top just with a fan. And then the ability to move that heating, cooling from one space to the next, if you have the right combination of loads, is very significant. And that's it. That's all I had, but let's open it up again. Anybody else out there have questions or comments? We have time. It's 11:38 Eastern, so we still have some time if anybody wants to discuss anything.
I had a question about the BRF you were just talking about. Is it since it's new to US in a way of like people adopting it, is it hard to find, is every HVAC contractor doing it, or do you have to find specialty contractors? How does that work?
No, it's becoming pretty common. I don't think you'll have trouble. I mean, you might have to shop around a little bit, but I know contractors in Cookeville that are putting in VRF.
Exactly. It seems like a no-brainer.
Yeah.
Except for maybe cost.
That's interesting. It does have a rap for being a little more expensive. And I don't know. I don't see those numbers. I asked Rick that, and he kind of poo-pooed it, but he's in the business of selling VRF systems too. So, you got to be a little leery. So I don't know. I would not expect it to come in on the cheap side for sure.
Glenn, just to follow up to Ruchi's question there, I mean, I know that those VRF systems are beginning to be more prevalent in commercial and industrial. What's the typical starting tonnage where that's a popular option? I mean, obviously that's not, or at least not that I've seen for use in residential applications. I was just wondering what tonnage and size of equipment does that layout actually begin to have some efficiencies that make it justified with the cost?
Okay, Ethan, you want to take that? You want?
No, go for it. I don't have a right answer for that. I don't.
Okay, sure. Now you can get a like 5-ton unit, and I mean, I expect they could downsize it a little bit. So now it's applicable to residential for sure. You just, you have to have that like cassette. You could set in a ceiling, but most houses don't have drop ceilings. And so, I don't know if you're going to set that in a plastered ceiling or not. It'd probably be a little hard to retrofit. And then it's got that blower unit. You've probably seen them. There are some motels, you start to see them a little bit. When you go in the motel room and you got that remote control, that's a VRF system. And so they've got that cassette that sits up on the wall. And I don't know about you guys' wives, but my wife doesn't consider that beautiful. Even though I might, because it might save me money on my utility bill, but it's not what I call designer chic. And so, if you're going to do it in a residence and hide it, then you're going to have to probably design it in, where you can put it above a drop ceiling and maybe run a little bit of duct work or a closet, or it could be under floor where you blow up, through floor registers, something like that. But a retrofit, in a residence, why, it's certainly doable. I'm not sure it would be acceptable to all of the residents of the house.
Well, that makes sense. Thanks for your comments there, Glenn. So just as a practical matter, probably more applicable to new construction than retrofits, correct?
Yeah, I think so. Now,
Yeah.
like if a big developer owns a big apartment building or office complex, I mean, he can pretty well do what he wants to. I mean, of course, he could run off some tenants, but like certainly in an office space, I don't think anybody really cares, so long as they're comfortable in their office, if there's a unit on the wall or, something gets added to the drop ceiling, something like that. So, the retrofit is possible. And as far as units, I know we've got about 50 or 60 slides in a VRF presentation. And so we couldn't, we just couldn't do all that here. But there's some tonnage information. I think 5 tons is like for the small. Now that small unit would be either heating or cooling. You couldn't do simultaneous. You got to get up to, I think it's 15, 16 tons before you can have the simultaneous heating and cooling. And you can pair up to 3 of those. So like for a large building, you could have blocks of like somewhere around 45 tons per VRF twinned up unit. And then you could have, you could have 10 of those if you had 450 tons. And, you just have to find the space on the roof or someplace to set the outdoor units.
Well, that makes sense. Thanks for the explanation there, Glenn. And, if there's sufficient interest in this, maybe it's a topic we can explore further with some dedicated training. And with that, is there anyone else that has any further questions on either the VRF or any of the other material that we've covered here today? If so, now's the time. Okay, well, we will take silence as no. And with that, I just want to say thank you guys for taking your time to attend today's presentation. This was the 5th and final in our series. We will be sending out a link to the video of today's training, along with all the prior sessions as well to each of you. Also, each of you will receive a survey just to receive your feedback, okay, on each of these. And this will also be an opportunity for you to critique the material that you've reviewed, or that you've received rather, and also maybe provide your input here concerning what other topics you may like to hear about in the future. And for each of you that's listening, please remember the Industrial Assessment Center, okay, that's offered regionally here from Tennessee Tech. It's chaired by Mr. Languri and Mr. Cunningham. Both support that program. So if you have an interest, go to their website, reach out to myself or either to Dr. Cunningham or Mr. Languri directly and book those assessments. They are able to do so even over the summer term. So with that, I thank you for your time and look forward to hearing from you. And I hope you guys have a great holiday weekend. Thanks again. Take care.